Ricominciamo con il secondo talk della giornata, Marco Bonzanini con Word Embedded NLP in Python. Marco Bonzanini sta anche seguendo e organizzando un meetup about Python and PyData in London. Oh, sorry, I should probably speak in English. So there's a meetup in London about data science and Python, and he's running every month. So if you're in London or traveling in London, I suggest you to have a look. And so we're ready to start. So a great welcome to Marco, and enjoy the talk.
Thank you. So this talk is about natural language processing, and yesterday we had fun with the workshop, the introduction to natural language processing for beginners. So this one is somehow a follow-up of the workshop, a more advanced concept on word embeddings. But hopefully this is still for beginners, so there will be some theory, but not too much. It's more about the general overview, the general intuition behind the embeddings, what they are, why we use them, and so on. So about myself, I'm a scientist. I'm based in London, and most of what I do nowadays is Python and text analytics. Some of my experience ended up in this book about data mining for social media, published with Pact Publishing. And as Stefania mentioned, I'm one of the co-organizers of PyData London, which is one of the biggest local user groups for Python. So we have a monthly event with a lot of nice people, and we are also organizing an annual conference, which is coming up in May. So in a few weeks, you can check it out. It's really interesting stuff going on. Now, word embedding. So the way this talk is structured, first the overall kind of informal introduction to word embeddings and the intuitions behind them, what they are, what we want from them, and then later on a bit of theory, followed by a little bit of practice in Python. So terminology, word embeddings essentially are vectors representing words. So these are all synonyms, word embeddings, word vectors, distributed representations. Sometimes you see also semantic vectors. This essentially means all the same concept. And why is this important? Well, just like in data mining, essentially the way you represent data is crucial for the success of your application. Also in text mining, the way you represent your text is crucial for the success of your task. And in terms of applications, really anything related to natural language potentially can benefit from using these word embeddings. So I just want to mention a few applications: classifications, recommended systems, search engines. So when you type in your query, and then the search engine has some interpretation, some semantic interpretation of your query, and then also machine translation and many, many more. This just to give you a brief overview. In terms of representing our data, I just want to mention a couple of options that are sort of well known, well understood in text mining. So the first one is called one-hot encoding. In one-hot encoding, essentially you have vectors representing words, and this is what they look like. So we have zeros everywhere, and then you have only one bit being hot. So essentially each dimension of the vectors represent a particular word, and then for the single word vector you will have the relevant position being switched on to 1. There's one problem with this representation, which is dimensionality. So the number of dimensions is huge. That's the size of the vocabulary. Another problem is you don't really have a notion of similarity between these vectors, right? Because only one dimension is switched on. Anyway, this is a fairly common option. And another one that I want to mention is the bag of words approach. That's used for documents. So with a bag of words, essentially documents are represented as vectors. So here you see a few documents, and also each dimension is representing a particular word. So in this example, document 1 has the word Rome coming up 32 times, the word Paris coming up 14 times, and so on. And here you still have the dimensionality problem. You have a lot of dimensions. But you start having some notion of similarity, because at least you can somehow match the dimensions between vectors. And these are fairly common, fairly well understood in text mining. Now, moving on to word embeddings. This is what they look like. So they're vectors of real numbers. And what do we want exactly from them? We want the number of dimensions to be much, much smaller than the vocabulary size, usually 200-300, that's quite common. And then we want to have some notion of similarity between words. So if you notice, some of the dimensions here between Rome and Paris, for example, are kind of close to each other. So Rome and Paris are similar. They're both cities. They're both in Europe. They're both capitals, and so on. So we want to capture these similarities. Similarly, Italy and France, they're similar. They're both countries. They're both in Europe. They're both nice places to visit, and so on. So a few dimensions are sort of close to each other. But also Rome and Italy have something in common, right? So Rome is the capital of Italy, so there is some sort of semantic relationship going on, and we want that to be captured by some of other dimension. And likewise between Paris and France, of course. So this example is a bit made up just to showcase what's going on with these word embeddings. And if we look at them in picture, so Rome and Paris, they're close to each other. They're similar. And then Italy and France, they're also similar, so they're close to each other. And if you notice, there's a kind of a direction, Rome to Italy, capital of, and Paris to France, capital of. So you have this semantic relationship being captured here. So this is basically the magic with word embeddings. So if you start with the vector for Paris, you add the vector for Italy, and you remove the vector for France, you end up with a vector which is very, very close to the vector for Rome. So you can map these relationships, semantic relationships, with these analogies. So that's the overall idea of how word embeddings look like. We don't have vectors yet. We have language, so we want to end up with vectors. So what's the main linguistic intuition behind them? The main linguistic intuition is called the distributional hypothesis. And this is nothing new. This is something that comes from the 50s, essentially. And in every word embeddings talk, you see this quote being referenced by this British professor of linguistics from 1957. You shall know a word by the company it keeps. There is also another reference that is maybe a bit more clear. So words that occur in similar contexts tend to have similar meaning. So in summary, we have a word, we want to represent the meaning of a word, and we can approximate the meaning of a word using the context, so using the surrounding of a word. So I'll just give you an example. This is a sentence: I enjoyed eating some pizza at a restaurant. And to make it more credible, I actually did enjoy some pizza last night. So we focus on what's important here. This is our focus word. And this is the company it keeps. So if we want to capture the meaning of the word pizza, we just look around it. So pizza is something we eat. Pizza is something we have at the restaurant. Pizza is something we enjoy. And then if you picture it on a larger scale, people describe the word pizza in many, many different ways. And when you aggregate everything together, you have the true deep meaning of the word pizza. Counter example, we have two sentences. So I enjoyed some pizza, I enjoyed some Fiorentina. So these are our focus words. And if you notice here, we have exactly the same context. So according to what I told you so far, essentially we're saying pizza and Fiorentina are exactly the same. So this is of course outrageous. But again, picture it on a larger scale. So people describe these terms with in many, many different ways. Some people might even not enjoy pizza. So that's how it is. Now, moving on with a bit of a bit more details on the theory. So word embeddings are the vectors, but we also say word embeddings as the algorithms to get the vectors. And it's a family of algorithms. And in particular, I want to mention word2vec as a popular option. It was essentially the first big breakthrough with these word embeddings. And this happened a few years ago, 2013. And these guys from Google, Thomas Mikolov and colleagues, they published a couple of papers, efficient estimation of word representation in vector space, and also distributed representations of words, phrases, and their compositionality. And the concepts from these papers, they ended up in what we know today as word2vec. So we need to get vectors, so we want to calculate this vector. So the goal is to learn word vectors. Now, if we look at things from a distance, everything in machine learning kind of looks the same. So we start with choosing an objective function. We initialize randomly our vectors, and then we run stochastic gradient descent until we get the vectors. So if you've done some machine learning before, maybe you've seen the same process in different tasks. So maybe what's interesting here is what's going on with the objective function. So again, taking the previous example, we have a word and we have the context of the word. So essentially our objective here will be to maximize the likelihood of the context word given the focus word. So we're going to end up with a bunch of probabilities that look like this. So probability of observing a context word given that we observe the focus word. So a few more details with this example to see how the algorithm is actually working. Same sentences before. We have our context word, we have our focus word, and we want to iterate over all the context words. So we start from the beginning of the sentence. I see the word I, given that I'm focusing on the word pizza, so I bump the probability for I given pizza, and then I move on. I see the word enjoyed, and I bump the probability of enjoy given pizza. I see the word eating, and I bump the probability of eating given pizza. And then we iterate all the way until the end of the sentence. Once we get to the end of the sentence, we move on to the next focus word and repeat. So I see I given at, and I bump the probability of I given at. I see enjoyed, and I bump the probability, and get a picture of what's going on here. So this is a nested for loop, and the core of the matter here is bumping these probabilities. I mentioned these probabilities, this conditional probability of a context given a focus word, and we haven't defined the probability yet, so there are some question marks here. What's going on with the probability? Now, to generalize, we call the focus word also input word, and the context word as the output word. We want the probabilities to be dependent on the vectors, so we can redefine the probabilities in this way. Probability of observing vector for a word given vector for the focus word. So in the general case, we essentially rewrite the probability in this way. Probability of output vector given the input vector. This is just to generalize the case. And we still haven't defined it. So the next step is to work on this. Now, we have this probability between vectors. Ideally, we want the probability to be high when the vectors are similar. So we have a notion of vector similarity here. And a fair option is to consider cosine similarity. It's quite a common way to compute similarity between vectors. One problem is cosine similarity is not a probability. So it's a number between -1 and 1. The next idea, we take the cosine similarity, we throw it in a softmax function, and the output of a softmax is a number between 0 and 1, so it looks like a probability, and it actually has a probabilistic interpretation. And if you want a big scary formula, that's how softmax looks like. So we have an exponential of the cosine, and then you normalize it over the sum of all the exponentials across the vocabulary. If you've done some machine learning before, maybe this is nothing new, and if you're new to this, maybe this one looks scary, so you can kind of forget about the details of this formula and just focus again on looking at things from a distance. So the process of calculating the vectors, essentially, we want to learn word vectors. We do so by using stochastic gradient descent, and we do it on the softmax probability. So this is the overall process. Here you have all the keywords if you want to look up for the details. And if you're not scared about this theory yet, there's a little bit of a twist. So these guys wrote some follow-up of the work to create distributed representations of sentences or paragraphs or documents. So the focus here is we can learn vectors for documents. The algorithm in the paper is referred to as paragraph vector, but then to reference word2vec, they also call it doc2vec. And it's basically the same process, so we have a very similar probability, but you see here the conditional probability also has a label, and the label could be a document ID, it could be a sentence ID, a class ID, it depends on how we want to aggregate these probabilities, but pretty much the same process. Okay. Now, word2vec became very, very popular because it was an academic success on one side, but also on the other side they released the tool, open source there's a tool written in C from Google to calculate these vectors, and they also released the vectors themselves. So they trained the vectors on the Google News corpus. So they have billions of words essentially, and they are already there. So you can use them. You can kill the training time to 0 essentially, and use the vectors from Google. The tool is written in C, and we care about Python. So in Python, there's this library called gensim for topic modeling. And what they do is they implement a lot of this topic modeling algorithm. So there's a lot of stuff for natural language processing, and it's implemented in a way that is very efficient on one side, but for us as developers, users, essentially the interface is super simple. So the punline for them is topic modeling for humans. So it's very, very easy to use. And this is just a screenshot of their GitHub page. So to get started, basically pip install gensim, or if you prefer, conda install gensim, and you're good to go. And I want to give you a couple of examples of real life kind of scenarios to use this word embedding. So first, this is some work that I've done with a client of mine. So they have a platform for recruitment. You kind of upload your CV on one side, companies upload a job specification on the other side, and then there is some machine learning magic to match the right people to the right job. And we did this little pilot to check out what's going on with the word embeddings. So we had a bunch of resumes. Each resume has a number of experiences, and each experience has a number of skills associated to it. And essentially, we treat our experiences as sentences, and the skills are our terms. So we ended up with a vocabulary of about 15,000 unique skills. For the coding side, fairly simple. So you import the word2vec class. We had our data, in this case, in a JSON line format, but it doesn't really matter. The custom part is the third line, so you need to write your corpus reader. And you can do so in a way that essentially yields one experience at a time. So you don't need to load the whole data set in memory. You just need to yield one sample at a time. And then you load it up with the word2vec class that is going to train the model. And I'm kind of hiding a lot of the details here on the last line. You can pass a few optional arguments to choose number of dimensions that you want, to choose the size of your context, to choose a couple of things. But you know, from a distance, this is what it looks like. So you train your model when you train your model, then you can look up for your terms. So, for example, given the word chef, we have a vector for chef, and here we see the vectors that are closer to chef. So chef is a cook, they're synonyms, so the two vectors are very similar. And then we observe basically a bunch of job titles or a bunch of skills in the kind of food industry, restaurant industry, and so on. So bartender and waitress, they're not really chefs, but they are kind of, you know, working together. So that's pretty interesting. And then the twist is this magic with the word embedding. So you take the vector for chef, and you remove the vector for food. You end up with a vector which is close to all these guys here, Puppet, Ansible, Salt, and Chef itself. They're all libraries and tools for DevOps. Okay, so same word, chef, used in different contexts, and playing with this vector arithmetic, essentially, you end up with the vectors that you want, and that's really really powerful, really meaningful, especially for us during the kind of exploratory steps. So we found these word embeddings to be extremely useful to understand our data, so for data exploration. And then later on, in this recruitment platform, we also implemented a lot of semantic interpretation of your queries, expansion, suggestion, and so on, recommendations. So essentially, people who use the system, they type in something, and then the system can understand what are the skills to suggest in this case. So that was really an interesting one. This one? You have vectors. You take the vector for chef, learn from your training data. You remove the vector for food. You end up with a vector which is similar, close to these ones. So there's a new vector. You don't have it in your vocabulary. But that vector will be very close to Puppet, DevOps, and then Ansible. That's what the data look like. So if you have a CV and you are a chef, your words will be similar to chef. But if you are a DevOps, you've been using Chef, you've been using Puppet, you've been using Salt. These are all names of libraries that are in the same space. Chef, Ansible, Puppet, Salt, they're all tools for DevOps. Now, on a lighter note, kind of a side project of mine, I like beer, I like data, I like Python, so I did the only reasonable thing to do. I put everything together. So there's a data set of beer reviews from Rate Beer, about 3 million. So many beer reviews about many different beers, and there are many different beer styles. So these are some numbers. You can see there are a lot of words. So beer fanatics talk a lot about beers. And the process here is kind of similar, but we're using doc2vec in this case. So it looks pretty much the same. Import the class, you have your data, this time it was in CSV, and then the custom corpus reader, the third line, will need to yield one review at a time together with the beer style in this case. If you remember, the doc2vec probability has an extra label in the condition, and the label in this case is the beer style for me. So I want to aggregate this review according to beer style. And then I load up the corpus in the doc2vec, and I train my model. And again, there are a few extra arguments. About 1 gigabyte of data. There's a bit of pre-processing, and then the training takes a bit of time. So on my laptop, it was a bit more than 3 hours. So the suggestion is remember to persist your model so you don't need to retrain every time. Don't close your Jupyter notebook without saving the model. Now we have document vectors with doc2vec. Okay, so model.docvex. And we want to check out how the styles are considered similar. So stout is a style of beer, style of black beer. And the similar styles are all kind of black beers here. So sweet stout, dry stout, porter. That's kind of what it is. So people describe different beers using words that are similar. And if you carry on with this list, you end up with other styles that are less similar, but they're still black. So there's a notion of color being captured. And if I want to check out what are the words that the people use most to represent this particular style. So stout, you know, it's black beer, so hints of coffee, hints of charcoal if you want, kind of burnt taste, roasted taste. So these are the most common terms for the style stout. And as a counter example, if we have a wheat beer, you know, lemony, orangey, zesty, kind of aroma, coriander seeds, and so on. So these are the terms used to describe this particular style, and it all makes sense. And just to go one step further, if you take all these vectors, so we have 200-300 dimensions, throw them in a principal component analysis, so we end up with 2 dimensions. We can map the styles on this plot here. So we have 1 dot for each style. We don't see any kind of explicit clustering here, but we still have some notion of similarity. So what I observed, essentially, similar beers, they kind of group together. So we have the dark beers on one side, and interestingly, the horizontal direction is the color. So all the lager and white beers, they are on the left, all the red and brown in the middle, and all the black, they are on the right. I guess this is a bit random, but that's what happened. Strong beers together, sour beers kind of on a different league, and then the lagers and the wheat beers, they are kind of all together. This was a bit of a toy example, a bit of a joke for me. So useful, of course, to plan my next pint. But again, this is really about understanding, having a deep understanding of your data. So essentially understanding how people talk about a particular topic. And it could be any domain model here. And I'm not showing any code, but I also used this data for a classification task. So given a review, can I predict what kind of style they're describing? And I noticed using word embeddings, you have much better results than using just bag of words or the kind of traditional approaches that you have in text classification. Okay, now kind of just wrapping up. So this is nothing new in a sense, because we've been doing stuff based on co-occurrences for a while, and just I want to mention a few examples. LSA, LDA, these algorithms, they've been around for a while, and they're all based on co-occurrences, but word embeddings learn with word2vec and or similar algorithms usually produce a much better representation of your data. So the traditional approaches are kind of outperformed. And word2vec also scales much better. So you have a large scale opportunity here compared to all these other traditional approaches. So there's a notion of efficiency. The first paper of word2vec starts with efficient representation. So that's the focus, efficient representation. Because they're based on co-occurrences, but there is no co-occurrence matrix in memory. So you don't need to load the co-occurrence matrix in memory. Vectors are learned as you go directly. So that's interesting. And I mentioned the softmax to compute the probability, and it has a complexity which is based on the size of the vocabulary. That could be very huge. There's a trick, anyway, that's called hierarchical softmax. I don't even remember all the details about the how you compute it, but there's essentially a binary tree involved, and you end up with a probability, with a complexity that is logarithmic rather than linear to the vocabulary size. So that's again this efficient aspect. Garbage in, garbage out, kind of classic in machine learning. So pre-processing is still very important. And your business domain is very important. So Google offers the pre-trained vectors for you. They're very useful until they're not useful. So the pre-trained vectors are trained on the Google News corpus. So this general purpose news, US-oriented kind of news, general English. So there's a good chance that your particular domain, your particular task is not general purpose news, general English. So you need to train your vectors depending on your particular domain. And if you have a very small data set, maybe word embeddings are not showing any particular interesting aspect. But if you have a few thousand words, and even more if you have 1 million words or more, yeah, absolutely train your own model. And to conclude, so all these word arithmetics, they look like magic. Really, it's a big victory for unsupervised learning. And the nice thing is you can kind of ignore all the theory and just use Jensen with a very nice interface. And yeah, I just want to mention, just want to say thank you to a couple of people. So Lev is a friend of mine who works on Jensen. He's also around the PyData London, and he gave me this T-shirt. So Jensen is sponsoring my outfit today. Chris Moody, I haven't met the guy, so he has a couple of great presentations on LDA and word embeddings and all the stuff, so you can check him out on YouTube. And if you want to know more about the theory, there's a lot of stuff going on online, especially these online classes with Stanford. They're really good. Okay, so this is essentially all for me. The slides are online. I'm easy to find online, and we have time for questions now, but I'll be around anyway today and tomorrow. So yeah, that's it for me.
Thank you, Marco. No? Are there any questions around?
Which are the performances, the standard performances of these things? Can you use them in real time? For example, for a colloquial interaction, for example.
So there's a training phase.
Yes.
And that it depends on the size of your vocabulary.
Sure.
And then once you have the vectors, if you want to compute similarity,
yes,
it's nearly instant. Yes,
okay,
yes. But the training phase,
yeah,
it can take seconds, minutes, months, depending on the size of your data.
Yeah, once the learning is done, so the
yes,
reply
yes,
is almost instantaneous.
Yeah, yeah, absolutely.
Thank you. Great talk.
Thank you.
Can you tell a bit more about the pre-processing steps? Like, I think it's very important to get rid of spelling differences or typos, or
yes.
Are there more? Or?
Yes, I very much agree. Pre-processing is still very important. In these examples, I only did basic tokenization and kind of lower casing, and that's it. I didn't bother with the stemming or stop or removal and so on. So you have an option to choose what you want to do here. For example, with the skills and CV, the first use case, we didn't have proper English. We didn't have like a grammatical sentence. We had just a list of skills thrown in as a sentence. So that's not proper English. But still, you can see the co-occurrences. Another option is to use a proper sentence, and then if you use a proper sentence, you can choose between passing everything minus stop words, doing some normalization, and you can observe some different results. I think the basic steps that you can kind of think of off the top of your head are all you need to get started. But of course, during if this is an R&D process, you will need some iterations. So just there's a bit of try and error to find the optimal solution. But yeah, you need to work on it a little bit. But it's not in particularly tedious, because if you have enough data, these approaches will pick up on these semantic similarities quite easily. You have more than 1 million words in your data, which is not a huge data set.
Really nice talk. Is there a link between the the vectors that you obtain with this method and what some people call topics? Want to hear that?
So you're thinking about LDA, essentially, kind of, yeah. Not much, not much. If you take the vectors after the training itself, you can cluster them and see what's going on. So that if you have a little cluster of vectors, maybe you have a topic. But the idea is if you do this arithmetic, so you sum and subtract vectors, you end up to kind of the concepts that you want to highlight. I think there is no explicit notion there. If you check out the videos by Chris Moody, he's been working on LDA to VEC, which is kind of on a hybrid LDA embeddings kind of approach, and that's quite interesting stuff. I didn't dig into the theory yet, I just checked the presentation. So that's maybe one direction that you might want to explore.
Hi, I have a simple question.
Yeah.
This dataset was the same language, I think.
Yes.
Or, yeah, with when you have a different type of language, for example, Italian, English, or more difficult language like Chinese, something like, how could you do similar metrics? You have to force to divide and do a ranking for different language, or you have to, you could mix in some manner.
So multiple languages in the same data set without a label.
Yeah.
Okay. I haven't explored anything like that. So I guess you need to somehow to label the languages at the very least, and the language identification is a fairly well understood task with a kind of 99% accuracy. So you can run a classifier and identify your languages. You mentioned Chinese. Chinese also has a problem with tokenization, which is very, very difficult, so that's another story. I've seen a few papers where word embeddings have been used successfully for machine translation. So you train your vectors for English and you train your vectors for Italian or Spanish. And the vectors, essentially, there's just a kind of a rotation going on, so that you can map the vectors quite easily, and they are very accurate with large data sets, but it's not really my usual kind of task. So I've seen something in that direction, but I'm not sure about the details.
Two questions. I missed a step because
Yeah.
I'm tired, I think. You said one of the important points was your vectors have much smaller dimensions in
Yeah.
the vocabulary. Is that something you force? You say, I'm going to only have 5, and then you do the gradient descent or the learning.
Yes,
force
you choose the dimension for these vectors, and as a rule of thumb, less than 100 dimensions is kind of not enough. Usually people do 200-300. More than 1,000 dimensions not needed. So it's about efficiency. So less dimensions means it's just easy to do maths on these vectors. Some people try to force a notion that each dimension has a semantic interpretation. That's not really the case. That's not what happens. In the examples that I showed you, it was a bit made up just to kind of prove the point, but it's not really, you don't have a semantic meaning for each dimension. And I finished the talk without saying neural networks. These models are based on neural networks. I chose to avoid the term itself, but you know, in neural networks, what's going on inside the model? Nobody knows.
Last question.
Because it is the last question, so
Yeah.
it's more
Please.
of a philosophical curiosity.
Yeah.
I think in some years ago there was a race to improve this algorithm to understand decently the human language.
Mhm.
And now that we've reached this pretty decent level of accuracy, there is a race from people trying to be understood by the algorithm themselves. If anybody has to do with search engine optimization, knows what I'm talking about. So do you think there is an effect of content writers starting to write targeting the computers instead of targeting other people, and so ending up having a lot of content which, if you read it, has very low value or very low meaning for the human who is reading it, but has a very high value for the algorithm who is reading it? So we end up in a world made for computers and not for humans.
Yeah, that's a very good point. So I think, you know, garbage in, garbage out. Your model is only as good as your data. If you have some strong bias in your data, that will end up also in your vectors. So with this Google News, you know, if you talk about this US-oriented Google News, so for example, Mexicans, they're very close as a vector. They're very close to illegal immigrants. That's a strong bias, right? And if you have bias in your data, that will end up in your vectors. That's true, and it's true also if you're a copywriter and you kind of force this bias to be there. There might be something going on, but there is some research also in that direction. So these biases are kind of easy to spot, and there are some options for treatment. I haven't looked at that, but it's a good point, and people are aware of that now. So when you train your model, before you throw it out in the wild, you know, you don't want an evil AI to be out there. You want to kind of check what's going on before, and hopefully you want to try to filter these kind of biases. But then again, you mentioned in copywriting, but not everything is about the web. A lot of companies, they have their own data, and they might be clean in different ways. So yeah, it depends on the application, on the data set, on everything. But it's a good point to keep in mind. Okay. Thank you.